Swayam Prabha. Digital India. Educated India.
Now, so the concentrations, every species has to be completely balanced. So when you do that, you know the concentrations have to be in what is that balanced situation when you are doing what is that the atmosphere conditions should be mimicked exactly. You have to have everything in place. Then you can measure the kinetics here. This is what we have built. Okay. Now you see, this is the spectrometer. Hey guys, don't get confused. It is highly confusing. Even for me, it is confusing. My student Amit Debnath has given, what is this? What is this? I was asking. Don't be confused. All that you need to focus is, where is my laser? What is that I am probing? Probing means identifying. What is that I am measuring? That's all your mind should be. How does it matter whether my light source is this or a big laser? Does it matter to you? You should not worry about it. Okay, let us see that. These are the mirrors here. 1, 2. And I told you OH plus some reaction I want to do. I will produce the OH using this laser. This is about 1 crore. I am telling you the prices because you should know how expensive is this experiment. Okay. And now here this is the ring down mirror. Sorry, these are the ring down mirrors. So the light comes from, this is one laser, this is another laser, and this comes through this. And now the light is trapped here. For you, light should be only this. You should not worry about whether it is a laser or some bhutam. No. How does it matter to you? But it matters to you when you come to my lab. A student by name Balla, who is a son of Shivakasi Fireworks, who was earning 300 rupees a day in those days, came and did this. Not Rajakumar with this experience. Rajakumar only provided money, instruments and all. So nothing is impossible, my dear kids, I am telling you. Okay. Karthikeyan can do, what's your name? Kamalesh can do. Lokesh can do. Vignesh can do. Ganesh can do. Yeah. Turn this side, Mr. Lokesh. I won't leave you. You're afraid of him saying your name? Hey, what's your name? You said Abhinandan. No, Abhinandan. Lokesh, you should not be worried when Karthikeya, what is your name? Sarath is sitting there. Because he is supported by Ganesh, Vignesh, Vinayagar. All the names are same. Okay. So watch this. So when you do this, see all these, please understand. I am putting one light here to generate the radicals, and I am also probing the radicals with something else, another laser. This guy cannot fire some other time. This guy cannot fire like this. They should be talking to each other. Hey, I am producing the radical now, better you go and probe him now. What is the point in probing you after you are gone from this classroom? Enna Bhaskar, enna maaringa pannanuma? Okay, neenga okkarunga kelunga. Okay, so we can go. See, what is the point? You see, if I come and teach this class after all of you are gone, what do you call that fellow will think that this guy is completely gone mad. He doesn't know what is he doing. நல்லா சாப்பிட்டு வந்தாச்சு எப்படி டைஜஷன் பண்ணுறது தெரியாது என்னென்னமோ பண்ணுறாங்க இவரு மென்டல் ஆகி போயிட்டாரு எனக்கு போயிட்டு என்ன கீழ் பார்க்கல போடணும்னு சொல்லி டிசைட் ஆகி கரெக்ட் தானே இட் மீன்ஸ் there is a saying, milk the cow when cow is milking, giving milk, not after that. So when the molecules are available, radicals are available, you probe at that time. But how do I probe? I need to talk to these two lasers with something else electronically. That is what is called your delay generator. Here somewhere, these two are connected using some delay generator. Okay, these two. What does it mean? Don't worry what is delay generator. What it will do is, it will tell, hey buddy, this is photolysis laser. You fire now, it will fire. And it will trigger this guy. Hey, you fire now, 0 time difference. It will fire. 0 time means what? As many radicals are formed, those many radicals it will identify, absorb. Absorption will be maximum because maximum radicals are formed. Are you confused? Any confusion? Are you lost? Right? That means I'm a good teacher, man. Wow. Okay. Hey, you have to cut this. Okay. They're my friends, they know what to cut and what not to cut. Okay. So I produce the radical here and I probe the radical here, the maximum concentration. Now, after some time, I will say, okay, you produce now, but you probe after 100 microseconds. Why am I giving? I will give time for this radical 100 microsecond time I will give to go and react with the people, other molecules. Because I am doing A plus B, I am producing A, it should react with B. You understand? I produce A, it should react with B. That means I am producing the A in presence of B. And I will say, hey, probe after 100 microseconds. Okay. Next one, next incident is, okay, hey, you produce now, you go and probe after 200 microseconds. That means 200 microseconds I am letting the radicals A to react with B. Next 300, 400, 500, 600, 700 up to 1 millisecond. What time scale I am talking about? Millisecond. Can you measure with the millisecond this one? No, you cannot. So, but I can measure in the lab. See the beauty. Okay? Abhinaya. Making sense? I know. Okay. So, now why this time lapse I have given? What is the kinetics? Kinetics is, after all, the variation of concentration of the reactant with respect to time. So, I am varying the time 100 till 101 millisecond. When I am giving more time, the intensity of the radical goes down because the guy is going and reacting with B. See the beauty? You understand, all of you? Allow more time for your interaction, you will become friends. Further more time, I don't know what. Okay, now, you understand? So, now the declinement you see over the temperature, over the time. That is what is your kinetics. See? Clear? Did your laser bother you to understand this? Did it bother you? No. So, my point here is, you can cut from here later on, okay? My point here, not know. The point here is, don't be scared by looking at something big. No. See what is it. Have a micro observation. One day my student came running, sir, it is not working, sir. Sir, I am doing something. I asked him, what has happened? He said, I don't know, sir. Go and find out. It must be a small thing, you might have done a mistake. He spent 10 days and he came back and said that nut is not tightened. That's all. I know that if I go there and tell him, he would never learn. Let him learn. We learn from the mistakes. How many times you have fallen down on the road while learning the bicycle? Don't tell me you did not learn. 2, 3 times, at least 10 times. These are all chipped off. Amma adi kudita the, Allah, fine. Then now you know cycling. Maybe she will participate in the race with Soundarya. Correct? With the support of Kartikeya. Yeah. See? You know, it is difficult to remember anything in short term. You have to have focus. That's why I spell out the names quite frequently. So that, yeah, I should not call her Soundarya and you Dhanalakshmi. That's not possible. You cannot become each, right? Okay, now onwards you can regard. Okay, fine. I mean, you don't have to cut afterwards. Okay. Now you know the variation how you do. So I'll show you what we have built. Look at this. Everything is built in line, indigenous, except the lasers. See, this is the place where the laser goes in and photolizes. And this is the place where the CRD mirrors are there and goes. And there is a PMT there. Here is the PMT. The laser comes from that side and it goes. And I talk to these lasers. This is one, where is that? I'll show you some next picture. Okay, several lasers are there. You see that? And by the way, it is jacketed. I can circulate the fluid to maintain the temperature in the cell. That means I can do the temperature dependent kinetics. So beautiful, no? Everything is designed here. Everything is designed here. All of this is my student's design. We sit, Okay, this is how it is, this is how it is, okay, we'll do it. It doesn't work. Do it, it doesn't work. Do it, doesn't work. Do it, doesn't work. Do it, work. At one time it will work. And it worked, now improve it. Improve it, improve it, improve it. That's how it is. See how much difficult it is to build such thing? You can see the quality there. Complication there. This is one. This is called cross photolysis. That means the interaction is, although 100 kilometers path length is there, interaction is only 5 centimeters. That means only 5 kilometers of path length is used effectively. That is good enough if the absorption cross section or molar extension coefficient of the radical is high. That space is good enough for it to absorb. But some molecules, they cannot absorb. It's like some of you. You teach 100 times, you don't get it. Then what teacher will come, first time he will tell you, second time he will say, hey, listen, then take a stick, what you call in Tamil? Huh? Perambura? Perambu, Perambu good, Pannada? Panna? 100 times, 100 times he will lie. So that means you need more time to overlap with the student. In that case, this will not work. You need to do the overlap like this, maximum time overlap, where the absorption is low. You are measuring the kinetics on absorption basis, right? You are measuring the kinetics on absorption basis. Therefore, you should see if the radicals are absorbing. If some of them are not able to absorb in this path length, the interaction is only this much, right? But here it is how much? It's too much. So, spend more time with the student. Give more time for the absorption. You understand? Okay. Now you see, this is what it is. Okay. You have, although experiment, this picture looks very, only this much interaction. No, actually it is much closer. Okay. Same thing. This is one laser which is producing the laser, radicals, and these two lasers are producing the wavelength to probe, and this is the delay generator which talks to both these, this one and this one. Triggering, electronic triggering. Hey, you fire, it will fire. Hey, you fire, it will fire. So you give the time lapse. And every time you give the time lapse, you make 100 pulses at that time and average it. You cannot say, hey, I have measured, so be it. No, you have to do the error analysis. If you measure, so it is correct. You measure my height, it is 6.3 and a half, 6 feet 3 and a half. But you measure, he will say 6.3.6 or something. Because you see, a parallax error. Your tape may be wrong. The way you measure is wrong. Many things. So you have to average many times. Now this is the chemistry point. I mean, mathematical statistics should come into picture. So this is what we have built. You see this? See this complication. This is the laser which comes, will go back. This is the laser I am talking about. 355 nanometer. This is the one which comes through this. And it comes all the way, and here is a PMT, photomultiplier tube. Oh, sorry, power meter. And this guy is a dye laser, it's a YAG laser pumped dye laser. It comes, this is the probe laser. I am talking about these two lasers. These two lasers are this one and this one. Okay, the cost of this complete equipment, close to 5 crore rupees. We have built. So what are we doing by spending 5 crore rupees? We are measuring the kinetics of A plus B, one on absorption basis. One is the radical, another one is a stable molecule. You can measure the kinetics of radical and radical too. See, I cannot ask, okay, I am producing radical A. I cannot say, hey, you only go and react with B, don't react with A. No, I cannot do that. If he wants to slap, he can slap that guy or this guy, or backside also. I cannot control, because you are fully energized, you don't know what you are doing. You have produced the radical, it reacts with everything. It reacts with another radical. So you have to take care of that also when you are measuring. Otherwise your measurements are absurd and the results will be bullshit. Understand? Okay. Now this is Amit, and this is the first paper in chemosphere. I mean, it doesn't matter, but it really, by the way, to build all this and to get the first paper, it took 12 years for me. But I never gave up. The moral here is not to boast about myself. Never give up if you have confidence to do. I know one day it will come out. It came out. There are many people said, hey, this guy is building only, nothing he is doing. And all that, okay, fine, thank you, Baba. Nice meeting you. But I know one day it will come. It came. And we never looked back. We do wonders using this. Clear? Okay. Now, see, guys, you should understand the complication that you can see here. Right? It's not easy. This is done by the students like you. Amit recently got graduated, he's going to Scotland, University of Edinburgh. See that? In England. Okay. Now, okay. Now let us talk about some chemistry. It's already 3. They want a break? You want a break? Sure? Oh my God. Okay. Let me have. You have some coffee there outside? 350, huh? See if it is there, I want some coffee. Little bit. I need some fuel. Okay. You are sitting, man. I am shouting, jumping up and down. Okay. Now you see what is this radical? What is the radical? HCO. Formal radical. In formaldehyde, remove one hydrogen. It will become. It is not easy. To remove the hydrogen, you need to spend lot of money, lot of things. So this is John Flad and myself we have done in the US. And look at this. What is the 613.8 to 615.8? 2 nanometers. 2 nanometers. And look at the resolution. It is 0.001 nanometers resolution. What does it mean by resolution? What do you mean by resolution? Resolution is, suppose the resolution what I said is 0.001 nanometers. The 2 peaks which are separated with a distance of 0.001 nanometers, I see that as 2 peaks. I see them as 2 peaks. If the resolution is 0.01, I see them as 1 peak. In principle it is 2, but what I can see is 1 because you don't have the high resolution. So your resolution of the spectrometer matters. So look at this. It is 0.001 nanometer resolution. And I told my student Srinivas to do this. Hey, do the measurement. And he measured up to here because you need to change the mirrors after that. So I said no problem. See the signature. Beautifully measuring. So litmus test is over. Right now we will do the chemistry. You understand? No, because I cannot say that I have built it is correct. I think that I have built a horse. If it happens to be a donkey, then what will I do? I can't ride on the donkey. Can I? People will laugh. Now this is the kinetics what we have done. Craigie intermediate is an intermediate which is generated when an olefinic molecule reacts with, ozone. It produces Craigie intermediate. You know Craigie intermediate is a deuterium, right? So, hey, don't mind, I'll have it, okay, fine. Now, such Craigie intermediates with pentanone, 2 pentanone, we have done it. Now, as I told you, I cannot produce Craigie intermediate in the reaction cell and say, hey Craigie, don't go and react with another Craigie, but only react with 2 butanone, it will not listen. You say, poda. It will go and react with itself, right? Let us see how we can do. Okay, this is the history, you don't worry, I can leave these slides. See, this is ozonolysis. It produces Craigie intermediate. My friend Craig Tradges in Sandia National Labs, if at all, he is the first one to identify this. If at all he gets the best recognized, he may get a Nobel Prize for this. Because it's a PIMS, photoionization mass spectrometer in Sandia National Labs using the synchrotron radiation. They measured it. So complicated. But once it is measured, I can do it in my lab now. See that? Okay. Now, so why 2 pentanone and 2 pentanone is a biofuel? Simple. Okay. We are using everywhere. Let us not worry about it. Now, how do I produce Craigie intermediate? I have some other method. Let us not worry about it. Now, I want you to realize one thing. What we produce here is, you see this? What is the concentration of Craigie intermediate in the red letters? Can one of you read? Karthikeyan, you read it? 4 to 5 range into 10 to the 12 molecules, radicals per centimeter cube, volume, concentration. Okay, what is the concentration of 2-pentanone? 2-PN. Right? So what is the difference you have seen in between these two numbers? Double? Your head. Or where solranga? Then? Abhinaya. What is the difference you see? Indumati. What is the difference you see? Madhumati. Madhumita. Who is that Madhumita? You. I forgot your name. Damayanti. Yeah? What is that? Bhanumati. Bhanumati. Yeah. She got angry. You see that? Oh, no, how can you call me that? I'm Bhanumati. Fine, no problem. Fine. There was a movie called Bhagamati recently. It's a pay movie. So, tell me, what is the difference? You see that? I want you to tell me before I finish. What's your name? Soumya. Soundarya Soumya. Oh my God. Okay. That means there is a 3 orders of magnitude difference. 10 to the 12 and 10 to the 15. There is called 3 orders of magnitude difference. Why is it done so? Think about it. Miss Music, Sangeeta, tell me. What's your name? Again music, oh my God, double music. Ilayaraja and Kiravani. Okay, fine. Tell me, why? Why do we do that? I tell you. Have you done one experiment which is called ester hydrolysis in the lab? Yes, there you go. That why? What did you notice there? Pseudo order. Head, tala. Next. Pseudo which order? Pseudo first order conditions. Actually, it is not first order. It is neither second order. It is in between. What do? You reduce the concentration by several times so that you can see the difference, change in the difference, only this one, not that one. Because even one radical reacts, there are 1000 radicals more, 1000 molecules more available. You understand? So we conduct the reaction in the pseudo first order conditions. Okay. Fuel is injected, I am charged. Now you see. Now I have carried out the reaction in such concentrations. What did we get it? Now you see simple mathematics we will do. This is second order reaction rate law, right? And if you look at 1 over delta kappa T and this equation y is equal to mx plus c. All you measure is delta kappa T. What is delta kappa T here? If you see number density times cross section of the molecule, that is concentration of the reactant times its cross section. Path length, cross section, you see concentration. All this, if you see that delta kappa T, if you rearrange the complete equation, what you get is 1 over delta kappa T. I am not jumping, I am trying to minimize the mathematical part, is equal to y equals to mx plus. If what you measure is delta kappa T for this reaction time, I have given reaction time up to 7.2 milliseconds. 1000 milliseconds is 1 second. 7.2 milliseconds have gone out and carried out the reaction. Now, when you do this, 1 over delta kappa you can calculate. So, by doing this, what I am trying, here you see K observed is K prime times sigma 360. What we measure is K observed. Why? Sigma, that is absorption cross section of the radical Craigie intermediate, if I measure, I may get something, you measure, you may get, depending on the experimental uncertainty. But if I get sigma independent absorption rate constant, I don't mind. You give me any number, it will fit. You understand? I will measure the sigma independent rate constant. What are we measuring here by means of absorption? We are measuring the kinetics. So, but I measure the rate constant which is sigma independent. I am absorbing at one wavelength. What is it? 360 nanometers. Okay, we want to, I don't mind, I don't want to know how much it is absorbing, how much light is formed, all that is independent. That means what I am trying to do, all my lasers and everything are only facilitators, but they do not influence the kinetics. Understand? How do you do is important, is not this one. What you measure is important. All these things are facilitating the process. You can have 100 errors there, but you don't want to carry the error into your measurement is the point. Okay. So now, in simple words, this, if you see what is this number density, and this is, it is defined as delta K and the delta kappa, and then this is K observed, K prime into what is K prime? K prime is defined as K observed by 360. That means this is the sigma independent rate constant is K prime. This is what we will measure. Okay. So, when you plot, so okay, we go back, delta K and delta kappa and 1 over delta kappa. You just measure this and fit this, this is delta kappa, is you can see there also. See, it is a sharp increase in the beginning and there is a declinement of the radical. See, if you don't understand the mathematics, that is fine. All that we are trying to do here is, we are measuring, see the absorption of the radicals. It goes down rapidly with the time because we are allowing the radicals to react with the molecular system. Okay. Now what is that we are measuring? You see, self-reaction. I told you, right? Hey Craigie, go and react with only this one. That will not happen. So you have to subtract the self-reaction. That is one of the possible reactions. Many reactions may be there. Unless it comes to our mind, we can't measure that. But at least in the small, in this simple chemistry, I am sure Craigie intermediates are there, plenty, and they can react with each other. See that? So this is what we have done with the Craigie plus this one, and I got what is that? K prime. This is sig. You can ask me, sir, why are you measuring K prime? Why not directly K observed? See this. There are people who have measured the absorption cross section of Craigie in 3 different studies, three different numbers. We have also measured. What we did, we have, see, now this sigma, this cross section we have measured and multiplied, what we got is 3.5 into 10 to the 6. But if you use this number, it will be different. If you use this number, it will be different. If you use this number, it will be different. But the rate constant, which is sigma independent, if I say, irrespective of what wavelength you measure. See, sigma, that is absorption of the radical Craigie intermediate, with 360 is some value, 370 is some other value. So it should be independent of that. That's what I am saying. What laser you use, what wavelength you use, it should be independent of that. That's what we have done. Now you have the kinetics of Craigie plus Craigie, right? Now you see, now I want to see this one. This I have to incorporate, this already we have measured. So what is this? This is also second order reaction. This is pseudo conditions, and we subtract this self reaction and you derive all that. What you get is delta kappa. Again you have to measure 1 over K versus delta kappa and 1 over delta kappa. Now you see all of you should understand this. What is this time? This is the reaction time and this is the absorption of the radical at low time delay and maximum time delay it is. So it declines in an exponential fashion. You see that? And when you increase the concentration of the radicals, this is what you get. Concentration of the reactant. Obviously, when you increase the concentration of the reactant, that is the B, A plus B out of A plus B, if you increase the concentration of B, your reaction should be faster. That's what we have noticed. This is 0.19, next one is this one, and next one is this one, and next one is this one. You can see the slope rapidly going down. Clear? Okay. Now again, we have one thing I want you to see. Don't remember these numbers. When some data is presented, you should see the essence of it. You see this? What is this temperature? 258, 278, 298, 318. Okay. This is the concentration of PN, 2 PN. Look at these numbers. With 258, this is 318. That is 60 Kelvin, right? The rate constant is going down. With the increase in temperature, the rate constant has gone down. What does it mean? What is the kinetics? What class you have studied? In the classes what you study? Increase the temperature, rate of the reaction goes up. But it is not happening, it is happening in the other way. You see that? That means some other chemistry is happening. You need to understand that. See, with the increase in temperature, rate of the reaction would increase, but it's going down. Why? We will see that. Okay. And but given temperature, if you take any temperature, with the increase in concentration of the reactant, rate constant increases. That's what we have seen. The declinement in the what is that? The slope is increasing with increase in concentration. That is intact, no doubt. But this one, you see that this is going down at every temperature, every concentration, and with the temperature. That you have to be very carefully observing it. Okay. Now you see, this is Pn concentration versus pseudo first order, and if you plot all of them, you get the data for all the 4 temperatures we have measured. Now you fit the data, you get 4 data points, and you plot the Arrhenius plot. What you get is your temperature dependent rate constant. It is simple. It is the concentration versus K. You fit this data, you get 4 data points now. Now at each temperature, 1 rate constant what you are getting. So K versus L and K, L and T, what is your Arrhenius plot? Okay, that's what we want to show you. Now, I told you in the beginning, we do computation also, right? I will not get into those details which will bore you. But I want to tell you, this reaction is reacting, it goes in several ways, so many molecules are formed. Which is the stable one, which is the most feasible one, you have to see. This particular thing is most feasible. See, you see that. Next one. See, this reaction channel is going down. The lowest energy channel is always good. Now I will answer you. Why the rate constant is decreasing with the temperature is, the reaction is, see, this is the reactant with another reactant, right? If you say this is 0, this line is 0, the activation energy of the reaction is negative. Can you believe? The activation energy of the reaction, but what you have studied, this is the reactant, this is the activation energy, activated complex, therefore the energy is this much. But this is a negative energy. So how does it happen? These two react and fall into a valley and form a complex before going into the transition state. That means this is the transition state. So this is falling into a valley, and the energy that is released in this process will be used to cross this barrier. Same thing here. It falls into a barrier, valley, and it crosses this. This much energy is good enough to cross this. So this is the lowest energy. Therefore it follows this path, and again it falls into the valley. But there is a transition state. So it uses the energy that is released from here, this point to this point, and that energy is good enough for this TS3 to be formed, and this radical is formed, this product is formed. What I am trying to say is, when the reaction is happening, it takes the lowest possible energy path. Why would it take? I mean, when you can copy and get the exam pass, why do study? That's what it is basically. But don't do that. If she fails, you will fail. Obviously. You don't know what she is writing, no? She may be writing some good notes. You think that is subject. That's all over. Finish. Both of you are gone. Okay. That's called karma. Whatever goes there, you will come to you. Don't copy from here, okay? Okay. Now, so this is, you understand this? This is the lowest. The problem is, you should understand when I talked about the rate constant is negative temperature dependent, immediately it should trigger you. Why is this? The reason for that is this guy. You see this? No transition state is directly formed. It is forming, they are falling in love with each other, they fall into the valley and then they come up little bit, again fall, again come, again fall, again come. So that is how the lowest possible energy path is followed. Okay. Now this is about absorption measurement. Then now it is the Arrhenius plot, theoretical rate constants. You see this, experiment is this. Theory, we have used 2 different theories. One theory is matching with this. Let us not get into those things. This is none of your business. Your business is to learn how you measure the kinetics of radicals with the stable molecules. See that? And radical reaction. You cannot do such reactions in simple laboratory. See that? Okay. Okay, fine. What do we do with this? I told you, faster the reaction, you find out how fast is the reaction and how long it will survive. That's all it is. Okay. Now you see, we have studied IO and MOE. This is IO radical from methyl alcohol, IO radical plus ethyl alcohol. You see, this is the positive temperature dependence, this is negative temperature dependence. Just one CH2 group in between. IO radicals we have done in the laboratory. Okay, we have produced the IO radicals. You know, CLO radicals are the culprits for ozone loss, right? So we have done IO radical reactions. Just this is methyl alcohol, this is ethyl alcohol. You see the contrast. Just by putting one CH2 group here, you complete kinetics changed. One is positive temperature dependence, another one is negative temperature dependence. Clear? Okay? So this is all about absorption. Okay, fine. Now, are you energetic to listen to me for another half an hour? Huh? No? No. You're bored. Come on, huh? No? Yes, no? All right. I'll tell them to wait for another 15 minutes. Don't worry. What is this? You are, as long as you are interested, I can speak till 10 o'clock in the night. I have no issues. With the same energy, I'll ask him one more cup. That's all. Huh? You want? You want coffee? Let us finish this. Huh? You sit Soundarya. What is this? Soumya, you should teach her. Kartikeya, you should tell her. Keep quiet. Don't talk rubbish. Huh? Sarath, you have to say, no, don't do this. Don't do this. Yeah. By the way, Soundarya's original name was Soumya only. I am talking about the heroine. Okay. Fine. Now absorption we have studied. Let us see the emission. We'll close it very fast. Okay. Very fast. I'll try to close by 4:10, 4:05, something like that. Some radicals absorb light and they, see, you know, radiative and non-radiative process, Jablonski diagram? Yes, simple. That's only we'll do. Okay, yes, super, very good. Very good. Look at this. Now hydroxyl radicals have produced same reaction system, but we have modified a bit for the LIF, for the easiness of the experiment. I will show you that. This is the you know what is this? Morse curve, harmonic oscillator, equilibrium, non-harmonic oscillator, equilibrium distance, and this V equals to 0, V equals to 1, this upper electronic state V equals to 0, V equals to 1. Very good. Now what I do? Can you go from here to there just like that? What do you need to do? What is that you need to do? She said, step it and go. Thermally you cannot do. If you heat so much, this guy will break down here because it's enharmonic oscillator. But it is simple. You excite it so fast before it realizes that it is gone there. Use a laser. Boom, you are there. Right? Then you see the fluorescence. Beautifully you can do. Now you want to see this. Now I excite hydroxyl, this is hydroxyl radical chemistry. And I excited 282 nanometers. Okay? 0 to 0, 0 to 1 transition is allowed. Now that guy is fully drunk. It has to come out. It will dance. Sometime it will come out. How it will come out? You see. Now 1 to 1 is 308 nanometers. See, we have excited at 282. It is coming out at 308. That means it has lost energy to the surroundings. For sure. But some amount of energy will be a non-radiative transfer. Okay. Then 0 to 0. 308 again. Results allow transition. So now use this principle. Excite at 282, see the fluorescence at 308. That means you can excite the radicals at 282 nanometers and you know for sure they will emit at 308 nanometers. So you can measure the concentration of these radicals by measuring the fluorescence here. Simple? Correct? You don't need to go and count. You will go and count? No. 1, 2, 3, 4, no, you cannot, 10 to the power of 16. Now, if you generate the radical and measure the fluorescence, you just measure the fluorescence at 308. If the intensity is gone down, that means it has reacted with the system. So what does it mean? You produce the radicals along with A, B. Your A is OH now, not Craigie anymore. You produce here and excite them at 282 and catch with you put a photomultiplier tube for the fluorescence and ask the radicals you are producing the radicals at one wavelength and excite at 282 and you vary the delay. And every time you are giving, this is the reaction time. Getting the point? What's your name? You lost? Looks like, huh? Narendran, you told me, yeah. So you are producing the radical, you are probing here. What is the probe? You are exciting at 282. All that you are doing is exciting at 282. You are producing the radical at 248 using excimer laser. You produce the 282 nanometers using another laser and you vary the delay. You measure the concentration decay with respect to time. There you have measured the absorbance, here you are measuring the fluorescence, emission. Both way you can measure the concentrations of the radicals. Craigie cannot fluoresce, OH can fluoresce. The radicals which cannot be fluorescing, their chemistry can be done with CRDS, cavity ring down spectroscopy. The radicals which can fluoresce, you can measure using laser induced fluorescence. This was invented by Richard Zaire from Stanford. He should get a Nobel Prize. Okay. Now, you see that. This is the cell. By the way, this cell, what I did, I went to US, nobody could do here. I went to US, I sat with a glass blower, asked him to make 2 and put it in my carrier and came here. Hey, you have to cut this, these things cannot be, okay. And so in the airport they caught me. Hey, what is this, professor? What are you doing? What are you? Who are you? And I said, professor, what is the experiment? Sir, you have to buy and pay taxes. No, it cannot be sold. One glass blower, somehow we managed and brought it. So those cells we are using here. Okay, right. This is the cell. This is see, I tell you what it is. See, where is that excimer laser? Yeah. See, this excimer laser produces the hydroxyl radical here. This is the way for that. Sorry, this is the way. There, one window here, there is another window there. One window here, there is another. One window bottom, one window top. 6 port cell. That's what it is. You see, 1, 2, 3, 4, 5, 6. So this laser, this 248 nanometers. You hydrogen peroxide, you know, H2O2. You dissociate at 248 nanometers. It will produce 2 hydroxyl radicals. Clean dissociation. Quantum yield is 200% there. Okay, and then radicals are there, you excite them by 282 nanometers, 281.9 nanometers. That means you talk with this guy between these 2 lasers. Same experiment, one is emission, one is absorption. And now you would see the emission, now you say, hey, you probe after this one, you produce 282 after 100 microseconds, 200 microseconds, 300 kinetics. This is what we have done. Nicely we have done, okay. I'll tell you. These are all rest of the things. Now this is the cell. You see that? This guy. This is a photomultiplier tube. You have to see how many wavelengths are there. 248 to produce the radical, 282 to excite them, and 2308 is producing. So you need to record only 308. So put a filter. This is what we put a filter here and photomultiplier. It only records only 308. I want the fluorescence. By the way, I told you in 10 minutes, 5 minutes time, but it took 14 years for me to do this experiment, get this signal. I joined in 2006 May. 2020 I got the first paper here. See how much pressure it will have, right? Government is giving money, I have to produce the data. And peer pressure, all nonsense comments. But I never gave up. Never. You want to do something, sky is the limit, you do it. This is the information to you. Okay, now, we have already talked about it. Now you see, this is the reaction what we have. When is the 2021 we published the first paper on this. Avinash Kumar is in Finland, Kaushik Mandal is in an industry, and it's me. Okay. Now, this reaction, why this molecule, let's not worry about, let's forget about it. Now, why this temperature range, this is the close to 310 maximum atmospheric temperature and it goes to 280 negative temperature 278. We have gone all the temperature conditions and all that we have managed. And you see all that you have seen, you see here is, what is this? Time versus fluorescence intensity. What that means? Hydroxyl radical I am measuring in the presence of the reactant with several concentrations. There are, this is without anything, this is 1, 2, 3, 4, all 8, 1, 2, 3, 4, 5, 6, 7 plus 0. This is C1 is 0, no reactant, just OH declinement. That also you have to subtract, otherwise you have to account for that, right? Now, if you fit all this, you get 8 lines here, 8 points in each line, and you do this reaction at whatever temperatures you want. How many? 6. You will have 6 lines here. Each point, each line, if you fit, this is the concentration versus K prime. If you put this, if you fit this data, what you get is K prime. K prime versus concentration, there are so many concentrations. So you can see each line will have 8 points. 1, 2, 3, 4, 5, 6, total 8 will be there. Okay. Yeah, here one more will be there somewhere. Okay, total 8 points. That means, sorry, 7 points will be there because that will not have. You can see 1, 2, 3, 4, 5, 6, 7. Yes. So you fit this data, all 7 lines will come in one line because it's one temperature. Like that you have varied 6 temperatures. Now you fit this data, you will have 6 rate constants versus temperature. That is your Arrhenius plot. What you study in the textbook is temperature versus rate constant. That's what I am showing you here. Okay. Now you see, now I know how many hydrogens are there here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens. So 10 transition states should be there. All 10 we identify, and you can see 6 different transition states. 2 can be same. These out of these 2, both of them will be same. Both of them will be same, like that. Okay. Now computationally you can say which hydrogen is contributing more to the reaction. Experimentally you can say by doing the isotope labeled reactions. That is expensive, so computationally we do very cleverly and compare. You see, again all transition states, which one is the lowest one? This one. What is that one? TS6. Where is TS6? This is the one. Where is that one? Somewhere here. Yeah, that's right. This hydrogen, you see that? This hydrogen. So this is the highest contributing reaction. Therefore, I am sure this is also. See? Okay, and you can see this contribution of TX6 is very high, and this is called potential energy surface. You see, this reaction is submissive reaction. Please understand, very low rate activation energy. So they fall in the valley and then go up. This is called negative temperature dependence. Okay, inverse temperature dependence. Okay, now this is Arrhenius plot. See that? Okay, sir, you can ask me, sir, you have measured all this. What is that you are saying? What is the rate constant we have measured? Second order rate constant. What are the units of second order rate constant? Concentration inverse, second inverse. Concentration of OH radicals. Multiply with OH radical concentration. What it will be? Some number times second inverse. 1 by that number is some number seconds. What does that mean? That means, what I am saying here is, if I were to tell you clearly, K is equal to X concentration inverse second inverse. This concentration inverse is concentration of the OH radicals. Multiply some Y concentration, then this and this goes away. X times Y second inverse. X times Y second inverse. This is K. These are the first order rate constant, right? Now 1 over K is equal to this X, 1 by X times Y seconds. See some number. That means this is the units of this is what? This is what is called lifetime. That is, you can measure, you can estimate how long this molecule will survive in the atmosphere. Go back to our plan first. If you travel for 10,000 years, if you can survive for 10,000 years, your molecule exists for so long. This data point will fall somewhere there. So all these rate constants are essential for you to mimic the atmospheric conditions or chemical composition of the Earth's atmosphere. I gave you 2 examples. There are several, but I'll skip. And now one more thing I want to tell you is, in this process we can do the product analysis also. That this is a flow system, but if you do in a static cell, suppose you want to measure OH plus A, you put B also. This B guy will also go and react with OH. OH plus B kinetics are known, but A doesn't know, you don't know. Loss of A with respect to A loss of A with respect to B you can measure using gas chromatograph or something. And then know the concentration versus time. Kinetics you can get. Drawback here is the reliability of your measured rate constant depends upon the reliability of B plus OH. Someone has measured it. It's not absolute method, it's a relative method. But the advantage here is you can withdraw the sample and do the product analysis. That I will show you. Here is the one. Put A and B. It is a simple reaction. I will not spend much time. See that? This same thing you can do. Arrhenius plot you can get, but I will show you the products. You can see in this reaction all the products using GCMS you can measure. I am not rushing. I am just avoiding the slides which are not relevant to you. You do a reaction of A plus OH and B plus OH in the same cell. Okay, and you measure once the kinetics are done, remove B and do the reaction in the cell and take the sample and inject into GCMS. Okay, you can see all the products. And I also have GC-IR. I have integrated GC with IR. That means after elution it let into IR. This is thermo-IR, this is excellent GC. I have integrated these two, brand new GC I bought and drilled a hole and connected these and written a software for this. We have, by the way, all the data acquisition software was written by my students. Nothing is commercially available. It's custom made. You understand? You have to talk to the laser, you have to do that, you have to get the data, it goes to the data acquisition system, you have to convert the digital data, analog data into digital data and take all the, see it's all not easy. Okay, GCIR, why GCIR? Whatever samples whatever products you have missed in MS, you can find in IR. Whatever you have missed in IR, you can find in MS. So these complement each other. Okay, you can see. You know what is the sample compartment size? 150 micro cubic meters. Very, very tiny. How much from the column it comes? Very tiny, right? That we grab and analyze in the IR. Very expensive this is, okay? About 2 crores this equipment. So once you know the products, you can propose the mechanism of degradation in the atmosphere. In the process you can see how much, see you have taken the reactant only this reactant. See how many are all the red color compounds are stable compounds formed in the atmosphere. All of them we identified in the gas chromatograph. What does it mean? You may think that you are releasing only one compound. What you are doing is you are creating a mess in the atmosphere. Okay, fine. Okay, I'll skip all this. Okay, well, all this is we don't need. Finally, I'll go to some place where I'll close this here. Okay, shock tubes and all combustion I'll not talk. Well, see this? This is the one side, and see, I'm very proud to present to you. This is southeast and northwest corners of the lab. See that? This cost of this lab is close to 20 crores. All of you are most welcome to come and see my lab. Okay? Yeah. And take home is the complete fate of a compound in the Earth's atmosphere can be investigated in our laboratory using laser based supersensitive spectroscopic tools. Okay? Oh, again no. No, I will not start again. But I will show you something to the hey. Finally, I will show you. This was my group for quite a long time, and okay, and finally, thank you. Okay, I'm done. 4 o'clock, 4:02. Okay, students, you can stop recording. Yeah.
SwayamPrabha, Digital India, Educated India.